All right, here's the last most missed questions presentation for rotation questions number 2 for your multiple choice. Here's your first one. It's kind of a tricky question to figure out how they're wording it, but you can think of this as a yo-yo sitting on the ground, and this would be the inner cylinder on the yo-yo. They've got all these forces pulling on it, and they make a statement here about the force that they have pulling on it. Strings attached to the cylinder, so it can rotate without slipping on the surface at point P. So here's my axis of rotation. That's how you should think about this. If this is my axis, then the only thing that will cause it to rotate around this axis is a torque. And we have to have a torque that exerts a force with a radius around this point P. It says a force F is pulled in the direction of the arrow D, so we're using this direction, and the spool spins, but does not roll across the table. Why would it spin? Well, it'll spin about its center of mass right here, so D does cause a torque around the center of mass, and it'd spin in place here. And it's not going to cause a torque around the pivot point for this object, or this little yo-yo, to roll along the surface. And the reason it doesn't do that is because if you extend this arm down, this dotted line, this is your moment arm. That's how we do moment arms. The moment arm would be 0 for this. So it says if the string is pulled with a force of 2F, which of the directions indicates a pull on the string will cause a spool to spin but not roll across the table? You should be thinking about the same thing that happened before. Well, we need D again so that moment arm is still 0. Kind of a weird question. Because if there's any friction between these two, you'd actually be able to, depending on how large that force is, you could lift that yo-yo up and it would start rolling. But the thing they wanted to look at is the moment arm there. Okay, this one has a bar that is released at an angle theta from the vertical, and it starts to accelerate down. And they just want to know what happens to the bar's angular acceleration as a function of theta. Well, if you look at what's happening here, the angular acceleration comes from the torque, and the torque comes from the center of mass acting. You can think of it as the center of mass, the force of gravity acting at this point right here. And that force of gravity is going to be related to your angle theta. These are opposite interior angles, so this is theta. And that torque, if we take that force of gravity, the torque from that force of gravity is going to be equal to your force, Fg, times sine of theta. And then torque, Newton's second law, is I times alpha. And so if I want to know what alpha is, alpha would be related to Fg times sine theta over your rotational inertia, your torque over your inertia. What would that function look like if I graph theta? Well, it looked like a sine function. And that angular acceleration is going to increase to a maximum when we're directly horizontal here. And when you're directly horizontal, Fg would have a 90-degree angle, sine of 90 is 1, so you'd have a maximum alpha. But it doesn't go at a linear approach. So many of you chose B here, that linear approach to your alpha. It doesn't increase linearly. It increases according to your sine theta function. That's how you get D as your answer, and it reaches a maximum right there. So if it's reaching a maximum, it's going to be horizontal asymptote. It's going to look like that. And then it would decrease again if that kept rotating underneath the horizontal. But if you got B here, if you graphed this, they just changed the problem like this, sine of theta on this axis, then it would be B. And that's how you'd linearize that data. We have another diagram here, lots of static equilibrium problems here. So this particular setup is a lot to read through here, lots of negligible things. But it asks at the end here, they measure the tension in this cable, and the students calculate the theoretical tension, and they measure the actual tension, and the measured tension is more than the theoretical tension. How could that possibly be that it would be more? Well, you would want a couple things happening here. You want more mass distributed towards the right. So one of the things that you could do, if this line here, it said the cable is uniform distribution. If it wasn't uniform distribution and more of that mass of that cable was towards the end here and less of it was towards the left side, then you'd have less of you'd have a greater torque due to the mass out here, and you'd have to have a greater tension force. If this mass was larger, you'd have to have a greater tension force, or if our rod had the mass not evenly distributed, so the center of mass wouldn't be right in the middle of it acting, it'd be somewhere over here towards the right side acting, and that would increase your torque due to the mass, and you'd have to increase your force tension force to counteract that. So which of these works? The radius of the hinge is not going to make an impact here. It's in static equilibrium and it's not changing any of your forces. Linear density of the short cable increases vertically. That won't make a difference because it's still going to be acting at this point. All of the mass below it will be acting at the same point. The linear density of the bar decreases with distance from the wall. Well, that would put more mass towards our pivot point on the wall here, and that would decrease your force of tension. D, the rotational inertia of the bar about the hinge is less than. E is your correct answer. Rotational inertia is greater than. And if the rotational inertia is greater than 1/3 ml squared, this is for a uniform rod. And if your rotational inertia increases, then that's going to be saying, it's another way of saying that you're moving mass of this rod towards the outer edge of the rod, and that's what would increase your force of tension. We have a ball that's released here. It's accelerating down, and it wants to know how does the angular momentum of the ball about point P change as a function of time. If you calculate your angular momentum, this is your velocity here. Angular momentum is just this. There's two definitions for it. It's I times omega, or it's mv sine of your angle theta between the two times r. This is the one that you would want to use here. So what's happening as it's accelerating down here? Well, the velocity is changing, and so is that sine of the angle. And you want to make a prediction here. The radius is changing as well. The easiest way to evaluate this, because there's so many things changing in this equation here, is if there was no gravity and this velocity was just constant here, because there's no external forces on it, just picture this being in space and that ball goes by the point P, the angular momentum has to be constant because there's no external forces acting on the system. And so if we consider acceleration in here now, and that velocity is increasing, if a constant velocity would give you constant angular momentum, if the velocity is increasing at a linear rate, that's what g would do. Velocity would be related to this equation, a times t, plus your initial velocity. Well, this is a linear relationship. Then your velocity increases linearly, so does your momentum. It has to increase linearly. And so your correct answer is this, C, linear relationship between those two. You could go through and choose a couple points here and actually calculate that out and show that it's a linear relationship. But the reason it's linear is because acceleration is constant. Okay, another acceleration one, or momentum one. If you look at this particular problem, it's kind of a complex problem. You've got two spheres that are rolling towards each other. They're magnetic. They're offset by just a little bit. And when they pass each other, they're going to stick together. And it says, consider the effects of friction and the spin to be negligible. That means there's no external forces on the system. Anytime you see that, you should think all momentum is conserved, angular and linear momentum. So which statement correctly describes any changes on your angular momentum? You should say it doesn't change at all. It's constant. So it remains the same for both of those. C is the correct answer. A uniform ladder of weight W leans without slipping against the wall, making an angle theta with the floor as shown. There's a friction between the ladder and the floor, but the friction between the ladder and the wall is negligible. The magnitude of the friction force exerted by the ladder on the floor that's what we want to solve for. So I would draw a free body diagram for this first. The wall has to have a normal force, but it can't have a friction force acting on it because the problem says that it's frictionless. The only other horizontal force would be that friction force on the bottom of it. So those two forces have to be equal to each other if it's going to be in static equilibrium and not move. And so that's what it means by saying without slipping. There's a normal force with the floor pushing on the ladder, and then a weight force of the ladder right in the middle of it. It's a uniform ladder. So what do I want to do? I want to consider how to solve this problem. And the best thing to do is consider your normal forces. Your normal force against the wall has to be equal to your force of friction. They're the only two horizontal components. And the reason is because your sum of your forces in the y or the x direction have to be equal to 0. Well, if that's true, you can simplify this problem a little bit by choosing your pivot point at the bottom. That'll eliminate two of your unknown vectors there. And then you can do torque equal to 0. And your torque equal to 0 would be the torque of both of these, your normal force of the wall in W. And that's right here. Normal force of the wall times the angle between the two times the distance. I just call L for the ladder from my pivot point to the force. and it's in the negative direction because it's causing the lyre to rotate clockwise. Your other torque would be the weight force, and the weight force would act at the radius 1/2 L, and it'd be multiplied by sine of 90 minus theta. That's how you'd solve this little right triangle right here. Well, sine of 90 minus theta is just cosine, so I could rewrite this. Cancel your L's, rewrite your sine of 90 minus theta as cosine, and then divide by sine, and you get cosine over sine, which is cotangent, and this is your correct answer, 1/2 your weight force times cotangent of your angle theta, and that's one of your choices on that problem. Let's look at another static equilibrium one. The uniform beam of weight omega, or W, is attached to a wall by a pivot at one end. It's held horizontal by a cable attached to the other end of the beam and to the wall, as shown above. T is the tension in the cable. Makes an angle theta, which of the following is equal to T. So we want to solve for a function of T in terms of W. So that little pivot right here, this can cause a force vertically and horizontally. So if I put those in there, Fy and Fx, we have two unknowns here, and we don't know which one or what either one of these values are, but we do know that the sum of the torques, the sum of the force in y, and the sum of the force in x have to be 0. Well, if the thing that I care about is this T here, it makes sense to choose this as your pivot point, and that'll eliminate these two unknowns, and I can get T in terms of W here. And so choose that as your pivot. Then your sum of your torques is 0, and the torques around that pivot would just be the torque due to the tension force, which would be the tension force times the distance. The radius arm would be L. I'll just call it the length for our beam here, times sine of the angle between the two, minus our negative torque here, our weight force times 1/2 L. And if you solve that for tension, L's cancel, you get W over 2 times sine theta, and that's one of your choices as well. Okay. Hope that helps for some of those static equilibrium problems. That's your last most missed question review.